Welcome to Direct Current Deep Dive, exploring the technical framework of Current OS, a MOOC designed to dive into the principles behind Current OS technical decisions and their role in defining the standard for direct current electrical systems, also commonly referred to as DC coupled systems, or DC microgrids. This video is part 3 of a 6-part series. Explore the remaining videos on the Current OS YouTube channel to continue learning about the world of direct current. In this video, we'll explain the underlying principles that drive Current OS's technical choices, leading to power management with Droop control. Resilience and convergence are at the core of the design. We'll see how Current OS installations are self-regulating, minimizing demand to the public grid, while stabilizing fluctuations for smoother integration with the public grid. Many people transitioning from AC often ask, what does DC bring to the table? There are areas where direct current can offer advantages that are difficult to achieve with alternating current. A helpful analogy is the difference between a tablet and a laptop. While both can send emails and stream videos, they serve distinct purposes. In practice, we might use a laptop for work and a tablet at home to watch Netflix. Though their functions overlap, tablets are often more convenient, fluid, and better suited to specific situations. The same principle applies to AC and DC. Partners in Current OS agree that DC offers more refined, sophisticated power flow management capabilities. These advanced features enable new services and possibilities that AC systems cannot provide as effectively. In the next animation, we'll illustrate this concept, rather than diving into technical detail. What can be achieved with direct current that is not possible with AC? DC allows voltage to act as a signal, guiding the behavior of every source and load in the system. When the voltage rises to the upper half of the nominal band, for example above 350 volts, but below 380 volts, sources tend to reduce their contribution. This could mean slower battery discharge, reduced energy import from the public grid, or even scaling back the contribution of photovoltaic panels once a certain threshold is reached. At the same time, when the voltage rises, loads respond by accelerating. For instance, electric vehicles charge at full power, and water heaters operate at their nominal capacity, effectively speeding up consumption. Conversely, when voltage drops, each source works to increase its contribution. Batteries discharge faster, within the limits of the converter's nominal power, and the system absorbs more energy from the grid as needed. Meanwhile, loads adjust by slowing down. Water heating and EV charging rates are reduced, aligning with available power. In DC systems, we refer to accelerating and slowing down to describe the dynamic adjustments of power flow. This highlights a key difference between AC and DC. In AC systems, most actuators function as contactors, toggling between on and off. Think about the day-night switch for a water heater. It's either on or off. In DC, thanks to power converters embedded throughout the system, every source and load effectively has its own variable speed controller. This allows for gradual, precise adjustments. The benefits are significant. By continuously adjusting sources and consumers, DC systems can reduce the power demand on the public grid by at least half, and sometimes up to 5 times. For the same building, this ability to dynamically balance supply and demand drastically lowers the required power at the grid connection point. In a world where public grids struggle to meet the rising demand for EV charging stations while also handling surplus energy from renewables, having a system that can continuously accelerate and slow down is a game changer. This capability has been demonstrated in numerous installations where Current OS solution has been operational for several years. To make it clearer, the concept will now be illustrated with a short animation. Let's consider a simple DC microgrid setup. It includes an AC-DC Current OS converter, a battery storage system, and photovoltaic panels in the parking lot, alongside an EV charging station. Within the building, there are typical loads such as lighting and a washing machine. Each device in this setup monitors the voltage on the common bus. The advantage of voltage is that it is the same for all devices, serving as a universal signal to guide their behavior. Based on the voltage level, each device reacts accordingly. This behavior is illustrated on the chart at the right-hand side. The vertical axis represents voltage, high voltage at the top and low voltage at the bottom. The horizontal axis shows the device's behavior, On the left, the device contributes power. On the right, it consumes power. Each source or load has a typical set point curve reflecting its behavior. Let's look at some examples. Photovoltaic panels follow a straightforward curve. They contribute all available power, regardless of voltage. However, when the voltage reaches a high threshold, their contribution begins to reduce. This is a typical behavior for photovoltaics. The EV charging station has the opposite type of curve. High voltage signals that sufficient power is available, so the EV charges at nominal power. As voltage drops, the charging rate gradually reduces until there is insufficient power for the vehicle, at which point charging stops. This reduction happens smoothly, avoiding abrupt transitions. More sophisticated contributors and consumers, such as the public grid connection, operate differently. When the voltage is low, power is imported from the grid. As the voltage rises, grid import gradually decreases and eventually stops, preventing unnecessary current circulation when two devices operate in parallel. If the voltage continues to rise due to excess power, the system begins exporting energy to the grid. The battery system behaves similarly to the grid connection. It contributes power when voltage is low, then gradually reduces its output and eventually stops. When there is surplus power, the battery shifts to charging. In this example, the battery is programmed to contribute before importing from the grid and to discharge fully before exporting power to the public grid. This setup supports an energy self-consumption strategy, although it can be adjusted for other priorities. Now let's look at the loads. Some loads, like EV chargers, can adjust their power consumption based on the available voltage. However, for critical loads like lighting, this isn't acceptable. They must operate at nominal power across the entire voltage band to ensure uninterrupted functionality. Finally, there are simpler loads, such as the washing machine in this example, which do not have gradual power adjustment. They operate at nominal power and stop entirely when the voltage drops too low. A small hysteresis is built in to prevent instability caused by frequent starts and stops. In summary, each source or load in a DC microgrid monitors voltage and uses a software-defined set-point control curve to determine its behavior. This flexibility allows the system to adapt dynamically, balancing power contributions and consumption efficiently. Let's see how the system behaves. Imagine this is a sunny day. The photovoltaic panels are producing power, raising the voltage to a stable level. The system naturally finds its equilibrium, providing enough energy to supply all loads, recharge the battery, and even export a small amount to the public grid. This ideal situation continues until the battery becomes fully charged. Once full, the battery can no longer absorb energy. As a result, the system voltage rises to a higher level, finding a new equilibrium. This forces the system to export more power to the public grid. A cloud passes by, reducing the photovoltaic contribution. The voltage drops, and the system adjusts to a lower equilibrium. At this new equilibrium, the missing power is drawn from the battery. Despite the change, all loads continue to operate at their nominal power, ensuring no disruption on the consumption side. More clouds arrive, further reducing the photovoltaic contribution, possibly to zero. The battery is pushed to its maximum output, but it's still not enough to power all the loads. The system adjusts to a new equilibrium by slowing down the electric vehicle charging rate, ensuring other loads remain powered. This situation can continue until the battery is completely discharged, at which point it stops contributing. The system adjusts to an even lower equilibrium where the washing machine is deactivated. The electric vehicle charging slows to almost nothing, while the lighting continues to operate at nominal power. Energy is now drawn from the grid. As a reminder, this is just an example. Through software, the system could be programmed differently to prioritize drawing energy from the grid, to charge the electric vehicle if it's needed for immediate use. Many other configurations are also possible. When the sun returns, the system reverts to the initial situation. The photovoltaic panels resume full contribution, providing enough power to recharge the battery. Since the battery has a nominal charging capacity, any surplus energy is exported to the public grid, while all the building's loads are fully supplied. We'll see now how microgrids can be extended easily. In this example, let's add a new load similar to an electric vehicle in terms of nominal power, but for a different purpose. Let's say it's a heat pump. What happens? In the theoretical diagram on the right, a new curve appears, and the system finds a new equilibrium. At this point, there is no longer enough power to charge the battery or export to the grid, but there is enough to supply the heat pump. This demonstrates how expanding a DC microgrid with current OS distributed control simplifies the process significantly. There's no need to adjust both the electrical and automation systems or involve multiple skill sets. The electrician simply connects the new device, and the system naturally adjusts to a new equilibrium. As mentioned earlier, all these curves are programmable. In this example, it's clear that not being able to recharge the battery might not be ideal. Adjustments could be made to better align with specific priorities or needs. One could imagine programming different curves to, for example, import energy from the grid to charge the battery. By adjusting these parameters, the system's balance can be shifted easily. While communication is used to modify these parameters, it is not critical to the system's stability. Unlike an AC microgrid, where losing the central controller's ability to manage current sensors, contactors, or converters can lead to instability, a DC distributed control system ensures stability even if communication is lost. The system maintains its equilibrium independently. In a building, however, the needs are more diverse, requiring a different system to meet those demands effectively. It's important to emphasize that this example focuses on DC microgrids for buildings, not photovoltaic farms, or frequency support for the grid using batteries, which are entirely different applications with specific requirements. Current OS principles are not relevant for applications like a photovoltaic farm, where the goal is to push maximum power to the grid with minimal losses. This distributed power control principle is widely recognized as the simplest and most effective approach for managing direct current electrical installations. It is increasingly gaining consensus across a growing number of direct current working groups and industry initiatives. However, in specific applications where voltage variations must be strictly minimized, alternative power control approaches relying extensively on communication-based solutions may be used. The implementation of a digital control system makes the electrical installation more dependent on the availability of this communication infrastructure. In addition, the evolution of both the electrical and digital systems over time will need to be managed in parallel, introducing new constraints and complexity. This concludes the power management presentation of Current OS. Want to learn more? Check out the other 5 Current OS MOOC videos covering an introduction to Current OS, voltage bands, electrical protections, pre-charging, and earthing. Thank you for watching. See you in the next video.